I kind of hesitate to cover this formula because this is not exactly the same formula that we'll use in the next chapter. In the next chapter or module, when we talk about finance, when we do this formula, we actually do it like this. So we have the principal times 1 plus r over m raised to the n. And in this case, we would have, so in this formula, even though it looks very similar, r over m, this has r over n. But in this formula, m is the number of compounding periods per year, whereas in this formula, n is the number of compounding periods per year. And then in this formula, n represents the total number of compounding periods, but here n times t represents the total number of compounding periods. So I'm just kind of giving you a heads up that the formula that I use in Module 2 is not exactly the same formula as this formula is here. So basically, if money is compounded, I don't want to spend a lot of time on this because we'll actually talk about this in depth in the next module. But let me just show you how you can use this formula to solve problems, because it is an exponential formula. If you have an amount of $2,000 and you deposit it into an account that pays 7.5% compounded quarterly, then how much money will be in the account after 12 years? Well, all you have to do to answer that is go to this formula and plug 2,000 in for the principal, and then for the rate put 0.075 because you got to convert the rate to decimal. And then this n here is the total number of compounding periods per year. So since we're compounding quarterly, that would be 4 per year, so we would have 4. And then the n times t would be the number of compounding periods per year times the number of years. So that'd just be 4 times 12, or 48. And then if you put this into your calculator, you should get $4,878.32. Now, I can ask you other types of questions here. Here I can say, how long before the account is worth $10,000? Well, in that case, then I'm just wanting to let the amount be $10,000, and then I want to solve for t, the time in years. Now, I could solve for n as well, but I'm just going to solve for, nt, but I want to solve for t here. So I'm going to put $1,000 in for the amount, $2,000 in for the principal, 0.075 in for r, 4 in for n, and then I have 4 for n here, and I'm solving for t, which is the number of years. So basically what I'm going to do here is, first thing I'm going to do is I'm going to divide both sides by 2,000. So if I divide, here by 2,000, that will make that 2,000 go away. And then if you divide this by 2,000, that'll just be 5. So 10,000 divided by 2,000 will just give me 5 here. Now, it turns out that 0.075 divided by 4 is actually 0.01875. So let's go ahead now and add these two together, and we'll get 1.01875. And then from here, I can now take the log. So I'm going to take the natural log of both sides. Now here you could use either log, common log or natural log. But I'm going to take the natural log of both sides. So I'll get the natural log of 5 is equal to the natural log of this expression. And then using my log property, I can take this exponent and write it out in front of the log. So I would have the natural log of 5 is equal to 4t times the natural log of 1.01875. And then I want to isolate this t. So what I need to do is divide both sides by the product of 4 times this natural log. So if I divide both sides by 4 times this natural log, I'll end up with natural log of 5 divided by 4 times this natural log. And then that will give me 21.66 years. And again, when you put this in the calculator, make sure you put the entire denominator in parentheses. And so it'll take almost 22 years for the account to grow from $2,000 to $10,000. Okay, now you'll see this formula also in the next section. This is the formula for if money is compounded continuously. That means it's compounded every instance of time. So basically, another way to think of that is that you have infinitely many compounding periods. So that's what that means. So if we do this problem where $1,000 is invested into an account at a rate of 6% compounded continuously, that tells me that we have to use this formula. How much will be available at the end of 20 years? And then how long will it take to double the initial investment? Well, the first question is pretty straightforward. You put in the principal of P, $1,000, and then it's going to be E raised to the rate, which is 0.06, and then times time, the number of years, 20. So you just plug this into your calculator, and you'll get that the $1,000 will grow to $3,320.12. Now, to answer the other question, it says how long will it take the $1,000 to double? So we want the amount to be $2,000. So we'll put $2,000 in here, put $1,000 in for the principal. The rate is 0.06, and t is the unknown. Well, then you can just divide both sides by 1,000, and you'll get 2 equals e to the 0.06 t. Then you can take the natural log of both sides, and so you get the natural log of 2 equals the natural log of e to the 0.06 t. And remember, when you take the natural log of e to a power, you just get the power 0.06 t. And so here you have natural log of 2 equals 0.06 t, and then just divide both sides by 0.06, and you'll get t equals the natural log of 2 divided by 0.06. And when I plug that in my calculator, I got 11.6. So it'll take about 11.6 years. Now, let me just mention this. Here, I took the natural log of e to a power, and since the base of the natural log is e, and this base is e, that allows me to just eliminate this and write the power. I couldn't do that on the previous problem, because here, even though here the base is e, the base of this expression wasn't e. The base of this expression was 1.01875. So I had to use a different property there to rewrite this. I'll wrap this up with a couple of other application problems. The formula for the measure of a Richter scale is given by a common log formula, x over x naught, where actually x is usually given as some multiple of what's called a zero level earthquake. So x naught is a zero level earthquake, and so the intensity of an earthquake is usually given by some multiple of this zero level earthquake. So in this example, the earthquake is given to be where x is 199,526,000 times the intensity of a zero level earthquake. So what we want to do now is find the Richter scale measurement of this particular earthquake. And it's really a pretty simple problem. What you're going to do is you're just going to replace x with this given value. So we'll have 199,526,000 x naught. And then you can just cancel those x naughts, and so all you have is just the common log of this number, 199,526,000. And then if you just calculate that on your calculator, just plug it in and hit the log button, you'll get 8.3. So 8.3 would be the Richter scale measurement of an earthquake with that types of intensity. Another example is in chemistry, determining the hydronium ion content of a sample of blood or other substance when you're given the pH. So the formula, the relationship between pH and the hydronium ion content is given by this formula, pH equals minus the common log of H3O plus. And so if you're given a pH of 5.41 and you want to find the amount of hydronium ion content, then you want to solve this log equation. Now the trick here, what you need to do is, I can write this in exponential form, but before I do that, I want to get rid of this negative. So all I have to do is just multiply both sides of this equation by -1. So if you multiply 5.41 by negative 1, you get negative 5.41. And that way, if you multiply this negative log by negative 1, it'll just change that to a positive. And that's what I wanted. I just wanted to get rid of the negative. Now, remember, the base of this log is 10. So if I want to solve for this H3O plus value, I just take 10, raise it to the negative 5.41, and it'll give me this value. So the H3O plus content would be 10 raised to the negative 5.41, and I actually got like 0.000039 for the content. And that pretty much completes the application problems for exponential logs that I'm going to work in this course. But I do have one gift section I want to give you at the end. I think you'll find it very interesting. It has to do with how pathologists determine time of death.